All right. Hi, my name is Zoe Monschein. I go to Greens Farms Academy, and today I'm going to be presenting my project, Exploring the Efficiency of Plastic Consumption by Tenebrio molitor larvae using FTIR spectroscopy. Oh, hold on. Okay. The global plastic production rate is 380 million tons of plastic annually. The world's plastic problem is one of its most threatening issues because it leads to pollution in the ocean, in soil, and even in humans. Polyethylene is the most common plastic polymer, and that can take up to 1,000 years to decompose naturally. So researchers are looking into faster ways of degrading plastic. One of these ways is biodegradation, which is the use of invertebrates to consume and digest plastic and therefore degrading it. In my project, I used mealworms, which are the larval form of Tenebrio molitor beetles, and previous research has been done on them where researchers have found that when they consume plastic and digest it, there is no effect on their gut health, and there is no microplastic residual remaining in their guts afterwards. They have also determined that the bacteria in the guts of these mealworms can be isolated and used on its own. And additionally, a graduate student at Stanford wrote her doctoral paper on a project she did where she fed two different plastic polymers, polystyrene and polyethylene, to groups of mealworms and measured their rates of consumption and tested their frass, which is their excretion, for microplastics using gel permeation chromatography. In my experiment, I decided to use Fourier transform infrared spectroscopy, or FTIR, which I have seen before in papers used on soil and leaves. But unfortunately, I had to outsource this process because our machine at school proved to be insufficient. But luckily, the lab also performed scanning electron microscopy on the samples. So those are the two images that I'm going to show you today. So I had three main purposes in my experiment. One of which was to measure the consumption rates of three polymers, polyethylene, polystyrene, and polyurethane by these mealworms. I also wanted to determine if microplastics would remain in the frass after digestion, and I wanted to determine if the plastic consumption hurts mealworm health. So as you can see in my table right here, I used three mixture experimental groups where the worms were fed a mixture of their polymer and bran, and then three experimental groups where they were fed just a polymer, and then a control group where they were fed just bran. So each of these groups had 100 larvae, and they were fed weekly on a Wednesday, where I fed them their food, and then they were left to eat it for 6 days. And on the seventh day, I removed the plastic and weighed it to determine how much they'd eaten. And then I cleaned out their tanks and starved them for 24 hours. And then at the end of that starvation period, I harvested the frass from the bottom of their tanks using diluted water, deionized water, and froze it until the end of experimentation. And then I fed the worms again. And this process went on for 10 weeks. And then at the end of the 10 weeks, I shipped off the week 6 samples to this lab in Houston for FTIR. And then I also performed optical microscopy on the week 5 samples to give me an initial idea of the makeup of the frass samples. All the samples were prepared the same way. They were poured into filter paper, washed with acetone, and then dried for 24 hours. And I also performed statistical analysis on the FTIR images with PRISM 10. So getting into my results, as you can see in these consumption rates, the polystyrene bran and the polyethylene bran had the highest average rates with 0.682 milligrams per week per larva for the polystyrene bran and 0.515 milligrams per larva per week for the polyethylene bran. As you can also see in both graphs, the polyurethane containing groups did not eat nearly as much as the others. And so for the interest of time in this presentation, I'm going to focus on polystyrene and on polystyrene and on polyethylene. As for the health of the larva, the larvae with diets containing bran, which are denoted by the dotted lines, had fewer deaths overall as compared to the pure plastic groups, and they seem to have had an initial shock to their systems, and then the death rates leveled out. which is promising. And then as for the pupa, I'm not sure if you can see this properly. Um, there were the mixture groups followed the control group in their pupation rates, but the groups that were fed pure plastic um, had hardly any pupa at the end of the experiment. And even after all the diets switched to bran at the end of the 10 weeks, the larvae still do not pupate. And so this has implications for the health of the larvae that were only fed um, pure plastic, which means that something in the bran contributes to the consumption rates and the health of the larva. Oops. Okay, so just to give you an initial look at the makeup of the frass samples, this is my optical microscopy from week 5, and as you can see, in the pure plastic groups, you can see that there are very visible plastic fibers remaining in the frass, as compared to the mixture samples, which were very similar to the control group, which is right here. And so this is our first hint that the mixture groups digested the plastic much better than the pure plastic groups. So getting into the FTIR and the SEM, this is the control group of bran. So there are notable peaks in the hydroxyl region, in the carbonyl region, and the fingerprint region. And so that's what we're going to be looking for in as we look at the experimental groups, and we're going to compare them to this control group. In the SEM, you can see that the visible image of this has a very grainy surface morphology, and the carbon, nitrogen, and oxygen levels of the sample are pretty consistent over, so these two different levels were taken in two different areas, and you can see they're pretty consistent throughout. So looking forward, for polyethylene, there were two materials identified in the sample. There was a cellulose part where this is likely digestion residual, and a polyethylene spot which had a 97% match to the reference sample, meaning that in this spot, the polyethylene was not digested fully. So we're looking at a partial digestion here, and there's no resemblance of the polyethylene spot to the bran spot. There's a big peak in the carbon-hydrogen bond region and two big peaks in the fingerprint region, but not, no, it does not resemble the control group. The polyethylene and bran mixture, however, had the same peaks as the control group in the hydroxyl region and the fingerprint region, and the carbonyl group, which is a little bit higher than the control, as you can see here. And a very low peak match to the polyethylene group as compared to the bran group, which had a 0.9982 correlation coefficient. In terms of the SEM of the three samples, the bran and the polyethylene bran mixture look very, very similar visibly, and that's reflected in their carbon, nitrogen, and oxygen levels, as you can see right here. However, the polyethylene looks a lot different than the bran, than the control group. And one notable thing about this is that the nitrogen level is almost double that of the control group. And one possible explanation for this is the fact that bacteria have something called a nitrogen metabolism that is used when their other digestion mechanisms don't work. And so that might be a reason why we see the high levels of nitrogen in this sample. As for polystyrene, we can see that there are peaks that do not match the control group, but there is an 87.7 ID match to the polystyrene reference sample. But the polystyrene and bran mixture has the same peaks as the bran mixture, as the bran sample, with the same peaks in the hydroxyl region and the fingerprint region. And that has a correlation coefficient of 0.9964 to the control group and a very, very low peak match to the polystyrene group. As for the SEM, again, the bran and the mixture look very similar, and the nitrogen level of the polystyrene group is almost double that of the control group. So again, we're looking at that nitrogen metabolism explanation.
Hey Zoe, you have just over 2 minutes.
Okay, awesome, thank you.
Yep.
So for just to review, the factors I was looking at in this experiment were the consumption rate, the microplastics in the frass, and the larvae health. So overall, the mixture groups performed much better than the pure plastic groups in terms of all three of these factors. They had higher consumption rates, better health, and less microplastics in their frass, if any. The polystyrene brand had the highest consumption rate. However, it wasn't as sustainable in terms of microplastics as the polyethylene. And as you can see in this picture right here, when the worms were consuming the polystyrene, they were creating microplastics, which goes against what this project was for, which was to make plastic degradation more sustainable. So polyethylene and bran had the second highest consumption rate of 0.515 milligrams per larva per week, and it was the most sustainable, a lot more sustainable as compared to the polystyrene because there was none of this creation of microplastics, and there was a better digestion, as we saw in the FTIR. So in terms of significance, polyethylene is the most sustainable polymer for this plastic degradation. And if we're going to scale up this rate of 0.515 milligrams per larva per week, we can, in one mealworm farm, they can hold up to 3 trillion larvae. And so scaled up, this is 80,000 tons of polyethylene degraded per year if fed to one of these farms. And so this has the potential to make a huge dent on the world's plastic production rate. And so future work to make this process more efficient could include longer times. So carrying on the experiment for longer and maybe performing an FTIR at week 10 to see if those digestion rates, if that digestion is better over time. Experiment with the bran to plastic ratio to see if less bran and more plastic could have the same results, and observing the changes in the health as the larvae become beetles, especially in terms of their reproduction, to see if they could reproduce and have healthy children. Thank you.